on. Hello, everyone. My name is Manvith.
I'm Sanjit,
And I'm Banu.
and this is our course Astronomy 101.
Today, we'll be talking about the Big Bang, which is our first lesson in this course, and the formation of the whole freaking universe. And it's in the unit 1 of the course, Formation of the Universe.
So let's get started.
George Lemaitre created the Big Bang theory. Approximately 13.8 billion years ago, all the matter in the universe was created in an event known as the Big Bang. He used Edwin Hubble's observation of the universe expanding and general theory of relativity, which is a theory proposed by Albert Einstein, which in simpler terms describe how gravity works and how objects interact with each other in the presence of gravity, to propose that the universe had a beginning point and expanded from that point, which Lemaitre called the primeval atom, which we now call the Big Bang theory. However, the universe did not expand from a single point. Only the observable universe, which we look up in the night sky with our eyes and the telescope, expanded from it, which we call the singularity. The part of the universe we can observe, which may be infinite, did not expand from a single point. This is because infinity cannot expand from a single point. For example, if you use a graph in Desmos and you keep zooming in or out, the graph won't stop since the numbers keep approaching infinity. It's the same thing with the universe since it is infinite. You can keep compressing it towards a single point, but it'll never be in a single point because it is infinite.
This means that the space-time fabric at the beginning of the universe is compressed, and as the universe expands, it's also stretched but not exploding. The space-time fabric concept is in close relation to the general theory of relativity. This theory states that space-time is not just empty space, but can also be thought of as a fabric. This fabric is not rigid, but can be stretched and curved by massive objects such as stars. The concept of space-time fabric provides a way to visualize how gravity works. Massive objects create a dip in the fabric of space-time, and other objects moving nearby will be influenced by this curvature, causing them to experience the force that we perceive as gravity. Space-time fabric was also very curved at the beginning because everything was super hot and dense, and having a higher density means that the curvature of space-time fabric, this is from the general theory of relativity. By hot, I mean really hot, as in 1,000 trillion degrees Celsius. That's 15 zeros. Near the Big Bang, time, the general theory of relativity, and the physics equations fell apart because of the impossible situation of the time being zero. It's kind of like the concept of the whole world being south of when you are actually at the North Pole with no north to go to. It's also worth noting that the universe may be eternal because before the Big Bang happened, there may have been another universe where it collapsed on itself, getting super hot and dense, which compressed into the space-time fabric, but then expanded again, stretching the space-time fabric.
So there are 10 steps to the universe. The first one being the Planck era, the Inflationary Era, the Electrolytic Era, the Particle Era, Nucleosynthesis, Recombination, Dark Ages, Structure Formation, Accelerated Expansion, and today.
The Planck era. This is the earliest stage of the universe, but our understanding of gravity is not enough to understand the effects of the gravity at the quantum level. The level where a particle can only take on small amounts of energy, called energy levels. This is also connected to the which is connected to quantum physics. It can also mean that the size where quantum effects take place. This is the quantum gravity wall where we are not able to get past.
Okay, the next step of the evolution of the universe is the inflationary era. So inflationary era is and quantum fluctuation is a theory that explains how the universe expanded and how quickly expanded. This theory also explains how photons from opposite areas in the universe could be connected. The theory also says that during the Big Bang, but before the universe was hot and dense, there was matter and energy still out there somewhere, and that the matter was stretching out very, very fast. It doubled in size around every 10 to the negative 37 seconds. That's 36 zeros. The theory is a way to explain why the universe expanded so much in a short period of time. Quantum fluctuations is where elementary particles pop into and in and out of existence, and there are random fluctuations in electromagnetic fields, which led to the minute temperature differences observed in the CMB from the Planck satellite. These minute temperature and density differences led to the formation of galaxies and clusters.
The grand unification theory describes the state of the universe when it had an extremely high energy and temperature, which caused all of these forces to combine. This theory is essential in describing the symmetries of the universe, mostly for gauge symmetries. A symmetry is basically just a system that remains the same after certain transformations. One example of gauge symmetries arises from the unification of two of the fundamental forces, the electromagnetic and the weak force. As the universe continued to cool and expand, it entered the electroweak epoch. At around 10 to the negative 36 seconds, the electromagnetic and weak forces were unified into a single electroweak force. The universe was filled with a hot, dense plasma of particles, including quarks, leptons, and gauge bosons. This was the grand unification theory, which states the unification of the three fundamental forces,
which are the electromagnetic force, the weak force, and the strong force. Then comes the particle era. During the particle era, which lasted until approximately 1 second after the Big Bang, the universe was still extremely hot and energetic. Particles and antiparticles continuously annihilated each other and created new particles. As the temperature dropped further, certain particle interactions ceased, resulting in the freeze-out of various particles. Freeze-out occurs when the rate of particle interactions becomes smaller than the expansion rate of the universe. As the universe expands, the particle density decreases, reducing the likelihood of particle collisions. Eventually, the rate of interactions becomes insufficient to maintain thermal equilibrium, causing particles to freeze out of the equilibrium state. The freeze out of particles depends on their respective properties and interaction strengths. For example, during the particle era, the strong nuclear force mediated by particles called gluons was active. As the temperature dropped further, the universe reached a point where quarks and gluons combined to form stable particles known as hadrons, such as protons and neutrons. This process is referred to as hadronization or quark confinement. Similarly, the weak nuclear force responsible for certain types of particle decays and transformations became less effective as the temperature decreased. The weak force freeze-out marked the point where weakly interacting particles, such as neutrinos, cease to interact with other particles on a frequent basis. The freeze-out of particles during the particle era is crucial for understanding the subsequent evolution of the universe. It sets the stage for the formation of light atomic nuclei through nucleosynthesis, which Banu will be talking about next.
Nucleosynthesis is the next stage. Around 1 second to a few minutes after the Big Bang, the temperature and density of the universe has decreased enough for protons and neutrons to combine through nuclear reactions such as nuclear fusion. This process, called nucleosynthesis, resulted in formation of light atomic nuclei such as hydrogen, helium, and trace amounts of lithium. Next, we're going to the Recombination Era, which is the next stage.
So around 380,000 years after the Big Bang, the universe cooled sufficiently for electrons to combine with atomic nuclei, forming neutral atoms. This event, known as recombination, allowed photons to travel freely through space, creating cosmic microwave background radiation. This is also when the universe stopped being the fate because of all the hot clouds of plasma, which allowed us to see the cosmic microwave background radiation caused by quantum fluctuations at the start of the universe, which led to formation of galaxies, superclusters, and photons.
Following the Recombination Era, which is the Dark Ages. The Dark Ages is a period when the universe there were no significant sources of light, and the universe was mostly filled with neutral hydrogen and helium. Gravity started to pull matter together, eventually leading to the formation of the first galaxies and stars. The reason why it was called the Dark Ages is because light could not go through the hydrogen and helium gas, and so we cannot look past the Dark Ages. Now Bonu will be talking about the structure formation.
So over a lot of time, like millions and billions of years, gravitational interaction between matter led to the formation of large-scale subspace galaxies, galaxy clusters, superclusters, and filaments. Dark matter also played a crucial role in this process, providing the gravitational scaffolding around which ordinary matter accumulated. And around 5 billion years ago, astronomers discovered that the expansion of the universe was accelerating. This phenomenon is attributed to dark energy, a mysterious form of energy that permeates space and drives the accelerated expansion. The exact nature of dark energy is still not fully understood. And today, the observable universe is around 46.5 billion light years in radius, going from the small structure of a quark to a proton and neutron to a nucleus, to an atom, to a compound, to a tissue, to an organ, to a human, to the Earth, to the solar system, to the Milky Way, to a cluster, to a supercluster, to a filament, to the observable universe, and finally the universe, which may be infinite.
Thank you so much, guys, for listening to our presentation about the Big Bang Theory, and hope you guys learned a lot. And so next lesson we will be talking about the structure of the universe and the expansion and the CMBR.
Thank you all. See you.
See you next video.
Okay, bye-bye.